Hello and welcome to podcast.init, the podcast about Python and the people who make it great. When you're ready to launch your next app or want to try out a project you hear about on the show, you'll need somewhere to deploy it, so take a look at our friends over at Linode. With the launch of their managed Kubernetes platform, it's easy to get started with the next generation of deployment and scaling, powered by the battle-tested Linode platform, including simple pricing, node balancers, 40 gigabit networking, dedicated CPU and GPU instances, and worldwide data centers. Go to pythonpodcast.com/Linode today, that's Linode, and get a $60 credit to try out a Kubernetes cluster of your own. And don't forget to thank them for their continued support of this show. You listen to this show to learn and stay up to date with the ways that Python is being used, including the latest in machine learning and data analysis. For more opportunities to stay up to date, gain new skills, and learn from your peers, there are a growing number of virtual events that you can attend from the comfort and safety of your own home. Go to pythonpodcast.com/conferences to check out the upcoming events being offered by our partners and get registered today. Your host as usual is Tobias Macy, and today I'm interviewing Pablo, Galindo, and Lysandros Nikolaou about their work on replacing the parser in CPython and what that means for the language. So Pablo, can you start by introducing yourself?
So I'm Pablo Galindo. I come from Spain, although I live in London right now. I've been a core developer for almost 5 years now. I've been centering my efforts mainly on the compiler pipeline. That includes the parser, the compiler, the AST creation, the garbage collector, although I've been working also all over the place. I work currently at Bloomberg in the Python infrastructure team, when we take care of basically the Python experience for all Python developers of the company. I think that's a great introduction.
And Lysandros, how about you?
I'm Lysandros. I come from Greece, and I used to live in Berlin, Germany for 4.5 years, but now I live in Athens. Yeah, I've been a core dev since June this year, and all my efforts were focused on the new PEG parser project. And prior to that, I had done some stuff on the GitHub bots we have in the Python team. Yeah, that's my experience with Python Core, and I'm currently working at Seafair, and that's an early stage startup in shipping.
And Pablo, do you remember how you first got introduced to Python?
That was actually even before. I think I was introduced first to Python when I was doing my PhD. I work on researching black holes. My background is physics. Basically, our software that we worked was some, C++ and CUDA and things like that. And I started to use Python for the first time which I think is very typical for scientific world, for basically gluing different pipelines of computing pipelines together and things like that. I fall in love with the language and I started to contributing. I think like most people with some documentation typos, which, many people think is not worthy contributions, but I think, they are, and everybody has to start with somewhere. And that's been a long road, but that was how I started with Python.
And Lysandros, do you remember how you first got introduced to Python?
I think it was back in high school when I had some projects in computer science, and I remember using C for the first time. And then after a while, I found out about this awesome language, Python, which is much easier than C, which was the language I had been using, knowing nothing about programming. That's where it all started. I fell in love with the language, like Pablo said. It was just amazing. A short while after that, I developed an interest in finding out how the language works. And that's how I got started working on internals and kind of wanting to find out further details about the language.
As I mentioned, we're discussing the work that you've both been doing on replacing the parser within the CPython runtime. So I'm wondering if you can just start by giving an overview of the role of the parser in the lifecycle of a Python program.
Basically, from a technical point of view, the parser is in charge from reading the text that basically composes a program and, let's say it in a very hand-wavy way, make sense of it. Basically, in the technical terms, it inputs the text and it will output an abstract syntax tree, which is a tree structure that then is used by the compiler to produce bytecode, or, in other languages or implementations, it can be a machine code or any other thing, right? But ideally, it will basically grab your text as it is and it will produce a tree out of it, right? But I think the technical term doesn't make justice to what the parser does. I think the parser encodes basically what the language is, right? Because all this particular tree that we're talking about, the abstract syntax tree, not only is something that compiler can find it handy because it doesn't have some of the things that are not important, things like commas and white space. The compiler doesn't care about that. But this abstract syntax tree basically holds the actual structure of your language. It's not only from a technical standpoint, but also from what people normally understand as Python. In some talks that I gave, I refer to the parser as the soul of the beast being Python here, because I think it's what reflects what people think about a language more than any other piece of the VM.
And in terms of the existing parser in CPython, what were the limitations of it, and how did that contribute to the overall complexity and technical debt that exists in the CPython codebase?
Basically, the limitations of the old parser were threefold. A problem of it was that there were some constructs in the language that were impossible to parse, and that means that we had to implement several workarounds that used to work around the fact that the parser itself could not parse those constructs. And that's things like assignment targets or like multi-line with statements. All those were impossible to parse at parse time. At the times of the old parser, they were handled at compilation time, at bytecode compilation time. And that's the first limitation. Then the second, not so much a limitation, but something that we felt we could do better, is that the parser used to output a parse tree that was then translated into this AST Pablo mentioned before, this abstract syntax tree. And we felt that we could optimize that. We could drop that intermediate parse tree altogether. And that's what the new parser does. It goes directly from a token stream from the actual source code to the abstract syntax tree, the soul of the beast. And also there were other things mostly related to LL1 parsers in general, like lack of left recursion, and that the parser was not actually expressing what the language actually looks like. Things like addition or subtraction. When the parser parses these things, it usually parses something like what addition will be made first. For example, when you have A plus B plus C, it's going to be A plus B and then outside that plus C. And the old parser did not used to do that. And we had an intermediate step that used to take these kinds of things like additions or right-hand sides and put them in the correct order. So all of these theory things now the parser handles automatically without the need for more intermediate steps.
So I've been discussing recently with Guka, like he's the actual release manager 3.9 and the author of Black, as many people will know him. And we have different views of what happened really. Tell my part of the thing. So I think 2 years ago, I was having lunch with him at Facebook, and we were discussing something that Black has a problem with, which is that when you have multiple context managers, let's say you say with something, comma, something else, and then you have a bunch of those. So the problem is that Black couldn't format those in a nice way because you cannot surround all of the groups of the context manager by parentheses. That's something that was not allowed. And sadly, that was a restriction of the old parser, right? This LL1 parser that we used to have in 3.8. And before, it doesn't allow you to write this. So he approached me, and because I was working on the parser at the time, he said oh, I have this problem in Black. If I could parenthesize these with statements, I could format them nicely one every line, right? The same way you format imports. You say import, open parentheses, and then you put a bunch of things separated by commas, and then a close parenthesis. And then I tried that, and it worked almost. A single construct that couldn't be made. And for doing that, I had to do a huge amount of hacks, all the tricks in the book to make the L1 parser kind of accept that. Sadly, I couldn't make every single thing work, particularly if you have a GL statement on your context manager, which is something weird, but you can do it. It couldn't work. And since then, I've been trying to find every single thing that I could use to hack around this. I asked researchers on parsers. I've been looking at all my my old books on parsing, and I've been battling with these multi-line context managers surrounded by parentheses for a long time. So when Guido, apparently this was something Lucas also mentioned to Guido, and when Guido started this project about okay, let's change the parser, right? I was super happy to start jumping in, and my one and single goal was this multi-line surrounded by parentheses with the statements, right? One could say that we've been working for a year to make that work. So I'm pretty happy to be in a world when this is now possible finally.
And I know that in some of the initial blog posts that Guido put out that covered some of his initial work on using a peg parser within CPython points to the fact that part of the reason that he landed on an LL1 parser when Python was new and why it has been in the language for so long is that while peg parsers did exist, they were too computationally expensive to be reasonable to include in the CPython runtime, and that with the evolution of compute and the increased power that most devices have, it's more reasonable to use that peg parser. So I'm wondering if you can talk a bit more about some of the options for other parsing strategies and what it is about the current point in time that makes peg parsers the right answer for CPython going forward.
I just wanted to say that basically a peg parser is not computationally more complex than an LL1. Maybe it is, but not in the sense that it's not feasible. It was not feasible back then. The thing to consider is that its space complexity is much, much worse because peg parsers and packrat parsing use a cache, and this cache needs to hold all tokens of the program, and that could be huge. And basically back then, memory was not that cheap. And as it gets cheaper with the years, programs or parsers or programming techniques that just use more space to trade time for this become more feasible.
Right. I think also kind of interesting, like at the end, the reason we went with a peg parsing is a bit simpler than probably what you already imagine. Even the choice for LL1 is very interesting because normally when you design a grammar to be LL1, what you want is to handwrite your parser because LL1 grammars not only are straightforward to actually do automatically generated, like you can automatically generate a parser very easily, but you can also handwrite your parser very easily. So that is normally one of the goals, but the old parser was not handwritten, was actually automatically generated as well, and also in a way that it was not a standard. I think it was the first of its kind. We do use like a special way of creating automata and then trimming them down, which is like by itself that is a known technique, but applying in the same way was quite new, I think. The reason he could do that is because the Python grammar doesn't have null production. That is basically a rule that doesn't produce anything. Like if you allow the empty string to be a valid rule in a grammar, you have null productions or epsilon productions are they are called, and that was not allowed. So we already have like an interesting choice of the parser, and we do like to automatically generate the parser for the source of truth that is the grammar. So when we started the peg parser independently of peg or other choices, we certainly want parser generator, right? We didn't want to write a handwritten parser. And peg is just a bunch of options. I mean, if you go to other kind of parsers, you can also find parser generators, but it's much more complex. Like we could have selected other technologies. I mean, I think it's also mentioned on one of the talks that we have made or one of the meetings that we have in the core team. Like one of the reasons we went with peg is because it's easy to understand what's going on. So it was easy enough for us to write a parser generator that is not insanely big. Because for instance, for LLK grammars and things like that, there is parser generators already, like Jack and all those. Bison Jack, I don't remember which one is the parser generator, which one is the tokenizer, but like there is already some of these. And the problem with this is that it's fairly much more complex to do one of these. We wanted to fine-tune the parser generator for doing different things. Like, for instance, now we have soft keywords. So implementing soft keywords in those may be easy, maybe not, but like we wanted something that we could understand, we could tweak to, specifically be made for Python. And peg was good enough, easy enough to understand. And, it also makes contributing to this a bit easier than it could have been if we have choose something different.
Yeah, I think that's a really important point that not only the generator itself is easy to understand, but also the generated grammar. So debugging it or the generated parser. And so debugging or working on it is much easier and opens space for new contributors to work on it because it's really easy to understand. Every function of the parser actually has the same structure and you can go through it and actually understand everything.
Yeah, and I'm interested in digging a bit more into the fact that it does pave the way for new contributors to the CPython runtime because it eliminates one level of complexity. So I'm wondering if you can talk a bit about some of the opportunities that it unlocks for people who might want to introduce new capabilities to the language that might have been too difficult or too cumbersome or too daunting to do before this parser replacement.
This is only my view. Probably other people in the project don't share this. I don't think it make it easier. I mean, maybe it does in some way. Like, for instance, the generation of the AST, like this is the part when it used to have this concrete syntax tree that we used to produce. We don't produce anymore, as Lysandros was mentioning before. But the thing that was translating that tree to the actual final one, the AST, was insanely big file. It's called python/ast.c in the Python source. And that was like, I don't remember, but it was like multiple thousands lines of code handwritten. And that was insane because, you need to reason about the number of nodes because it's very tightly coupled with the shape of the CST. So there is for loops that were reasoning things like, if I have 3 nodes, then it's an if statement. If I have 6 nodes, then it's a for statement with an else maybe. And that was like very difficult to understand. So in that regard, our parser may be much easier because from the grammar, it goes directly to the AST, and those are much more close. Like those are closer, right? So a contributor that understands something already about grammars and parsers may find certainly much easier to modify the grammar. But still, it's complex, right? Because you need to understand several things about how parsers works. In particular, you need to understand how peg parsers work, which is new, right? And unfortunately, one of the downsides of peg parsing is that sometimes when it works, it's very easy to make it work. But when it fails, it's quite difficult. You need to understand very well what's going on because peg parsers are very well known to have this kind of surprise grammar. Like sometimes you put something and then you don't understand why that thing is not parsing. We can go into examples. Maybe Lysandros can give some of the ones that we found. I think the net gain is probably 0. Well, maybe let's say it's positive to say, to stay positive in life, but like it's very close to 0 because, we gain the removal of this complexity of manually handwritten stuff. So now we have automatically generated C code, which is great. But unfortunately, I think we lost a bit on, well, maybe not. Maybe also LL1 parser, even if it's like honestly simple, it's also complex in the sense that you need to understand what is an LL1 violation to know why a rule that you have written doesn't work. So I don't know, maybe it's a positive change, but I don't think it's a great one or it's something super distinctive that we say, now with this parser, like, a contributor can jump in without any knowledge of grammars of Python and do a change. That probably, unfortunately, is still false.
Right. And implementing a language feature does not only include the parser. That's very important to know that in order to implement a new feature in Python, you have to go to the parser and then the bytecode compiler and then the bytecode interpretation. So in order for us to say that we've made it easier for someone to implement a new feature, we'd have to have an easier way to do all those things. But we actually don't. We've made, and that's arguable, but I think we've made it a bit more easy to tweak the parser, but we've done nothing about the other compilation parts and the other things that go into implementing something new. So yeah, someone might find it easier to work on the parser, but only that, maybe the parser generator as well, which the old one I find actually impossible to work with. But yeah, I think that's pretty much it.
I think now that Lysandros mentioned this, there is a good point that may be easier, which is that like before, if you get a syntax error on some construct that you're writing, so let's say you're writing a program, it's a syntax error, knowing where that syntax error is coming from was not trivial in the sense that because the LL1 like limitation, many of the syntax errors, for instance, were raised much later. Like the LL1 parser basically was parsing constructs that are not valid Python because it couldn't make the distinction in an LL1 way. And while we're translating the CST to the abstract syntax tree, which is after parsing, then we are saying, if the abstract syntax tree that we are generating looks like this is actually a syntax error. So we were raising a syntax error. And even though sometimes after the abstract syntax tree was created, in the compiler itself, or like when the compiler is actually reading that code, the compiler was also raising syntax error. So basically the definition of what Python is was spread between the parser, the AST, and the compiler, which is what's not great, right? Because if someone is trying to understand not only the grammar, but also the language itself, it needs to look at the whole compiler pipeline, right? Like parser, compiler, AST. Right now, although there is some small exceptions, but almost all syntax errors are raised now in the parser, so in the grammar itself. So if you go to the Python grammar right now, the new one, you could immediately see 99%, let's say, of syntax errors. So you know what is Python and what is not. Like if someone is now, for instance, creating a new implementation of Python, it's enough to go to this grammar if they understand the PEG formalism. So it's enough to go to this grammar and look at it, and they can immediately implement a parser that can be PEG or not, but they can know what Python is or how it's defined. They don't need to read C code, or they need to read 1% of C code, let's say, or something like that. I mean, these numbers are arbitrary, but like it's very small cases. Things like you cannot assign to __debug__. That is a valid assignment, except that the name is one of the reserved ones. The parser doesn't really know that. I don't think this is one of the ones that we have, but it used to be. But anyway, that's the kind of difference that people will be looking for. So in that sense, it's easier now.
And in terms of the overall process of actually making the migration from the LL1 parser to the PEG parser, because of the fact that this is so core to the actual processing of Python programs, I'm curious what the overall workflow was for being able to bring in this new capability into Python without adding any regressions or new edge cases, and the issues that you encountered in the process of all of this work.
Basically, the migration to the new parser is a multi-step process. If we talk very high level, then we know that in 3.9 there's both parsers, and the default one is the new one, but you can always switch back to the old one in case you find anything odd and you want the old to parse your program. And then in 3.10, it's going to be the only parser and the old one will be removed. In the actual development of the new parser, there were many steps and many efforts we made in order to make it as secure as possible, that it's not going to introduce any regressions. Basically, we first started out with trying to implement all of the grammar until we could parse all of Python. And then actually after that came the need for but finding edge cases in syntax errors, or edge case in syntax that's allowed and should not be, or that's not allowed and should be allowed. So there were many edge cases. We ran a test suite pretty regularly that used to try to parse all of the standard library. With every tweak to the parser generated, we used that test to make sure that the standard library still passes these tests. And after we were somewhat sure that we've completed all of the development on the PEG grammar, we implemented some scripts that downloaded basically a whole bunch of PyPI packages and tried to parse those. And then we identified some bugs there. So things like syntax errors in F strings that used to have some edge cases, and we hadn't already found those. And so after we did these tests, we were actually pretty confident that most of our syntax works. So most of valid Python, our parser can parse. That didn't do in that much detail is verifying negative input. And that means that it's pretty hard if you have a valid Python program to somehow make a sensible change to that syntax and render it invalid Python syntax. Actually take that input, make it somehow invalid, and then test on that in order to see if the parser actually denies that input. We did do some tests on that, mainly handwritten tests, in order to make sure that the syntax errors are correct, where the syntax error is correct, because the tree structure holds meta information about where the syntax error is. That was and still is something we may need to work harder on.
In this regard, there is an interesting fact that many people don't know, why this problem is so hard. Like, it turns out that if you think about, like, okay, imagine that you have two parsers, right? In this case, will be the old one and the new one. And then you say, there is any way to prove that these two parsers are equivalent. Surprisingly, like, computer science tells you that this problem is undecidable. This is equivalent to the halting problem. You cannot prove that two parsers are parse the same thing in the same way. You can also not only not prove that two grammars are the same, like you have two grammars, you cannot prove that they parse the same language. But like this goes so far that even if you have a grammar, it needs to be a context-free grammar, but a lot of them are context-free. Like you cannot prove that the grammar accepts all strings on its alphabet, like which is, I find it insane. Like that is undeceiable. It's a problem that cannot be solved. So it's a very hard problem because the only way to do this is basically what Lysandros mentioned. Like you need a corpus like big enough of good programs and bad programs, and then you need to test both parsers in this way. Like then every future validation will be basically made like this, right? Like you have some program that you know is bad, and then you test it with the old parser and with the new parser, and then you basically check, okay, is the rejection the same? Is the error the same? Is the position of the error the same? And so on, right? So fortunately for the good cases, like it matters the most because you don't want valid Python program to be claimed that is invalid. So for the good cases, we have the PyPI like corpus. So we have all the Python packages that people publish, which exercise a lot of grammar rules. There is some very weird things going on in the PyPI, right? But for the bad cases, like there is not a huge repository. Like people don't publish invalid Python programs. So unfortunately, we couldn't do that. The standard library though has a very good collection of testing and exercising syntax errors. So some strings and says, okay, is this invalid or is this other thing invalid? We find a bunch of errors by running those tests. So we are pretty confident that we handle negative cases good enough. But you also have this kind of very, very far and very small doubt that maybe you are missing something. For instance, without going very far, it turns out that we missed a valid Python case that was not exercised on any of the Python packages that we saw, which is that if you use a star unpacking, like the same way you can do a star variable equal and an iterable, and it maybe something else, right? Star variable comma b equal iterable. So in the same way you can do that, you can also do this star unpacking on with statements. And it turns out that we missed that on the release on 3.9. So it's fixed now. So 3.9.1 will be, you will be able to use a star unpacking on with statements, which is already weird because for using a star unpacking, you probably want you use a star unpacking when you have an iterable and you don't know how many items you normally have. With the statements, they normally don't have 600 context managers, no? But who knows? But yeah, that was valid, and unfortunately we missed that, but that is made. With all these words, what I want to say is that this is a hard problem. There is already discussions on Python Dev about how to make this easier, but any automatic way that you can think of is going to be very tricky. We tried some very good and promising tools. Like there is some work on top of Hypothesis Smith, I think it's called. It's a fantastic package. It generates random Python programs given a grammar. And, we try to use it. It's really impressive how it works. I mean, the whole Hypothesis is really impressive. Unfortunately, our experience, and this doesn't mean that the package is not good, but our experience is that it was not good enough for finding actual errors because the grammar space is infinite. Like the amount of possible valid Python programs is infinite. So exploring an infinite space when the errors are finite, I mean, it could also be infinite errors, but let's hope they are not, is kind of very difficult, right? The probability that you find something wrong is very complex.
Another interesting element of the fact that you're switching from the LL1 parser to a parser generator using a PEG grammar is whether or not the other implementations of the language, such as PyPy or Rust Python or Iron Python, would be able to take advantage of that fact and just use the PEG grammar that you've defined and then run their own parser generators to then use within their own runtimes.
I will pick this one. Unfortunately, many Python implementations, and I'm going to talk about for the ones I know. I think last time I saw, I could be wrong, but I think last time I saw PyPy is using a LL1 parser. So if they want to pick up, if we don't change the grammar in any way, they don't need to do anything. If we change the grammar in a way that cannot be parsed by an L1 parser and they were using an L1 parser, they will need to change. So, for instance, in Python 3.10, if the pattern matching PEP is accepted, that PEP is only possible with the new parser, with a PEG parser. You can use other parsers. It's not necessary a PEG parser, but certainly you cannot do that with an L1 parser. So if PyPy is using an L1 parser, unless they find a way to hack around, which maybe with that particular construct is possible, they may be able to maintain the L1 parser, but in general, implementation of Python is using an L1 parser, they probably will need to change to PEG or to something different. So for instance, I don't know what parser Rust Python is using. I think it's using third-party Rust library for that. So if that third-party REST library is based on LLK Parser, for instance, which is a generic one, they may be safe because you may be able to spread these new constructs on LRK. All these parser names are a bit insane. It's combination, so it's kind of difficult to pronounce for me. But if they are using something better than L1, they may be safe. If not, then there is the other problem, which is that probably they will need to translate the PEG grammar to whatever new grammar they have, but that's probably not super difficult to do. In any case, they can also switch to a PEG parser as well. But yes, this is not only a problem for Python implementations, this may be a problem to tools in the Python ecosystem that were relying on L1 parsers, which unfortunately is a bunch of those. For instance, I'm very sad to say this, but Black was using an L1 parser, so Black needs to change to something else. So Gukash, if you are hearing this, I'm very sorry.
Yeah, I just wanted to say that one step of the migration is that, and an important thing is that in 3.9 there's not going to be any new language features, so that tools that rely on LL1 parsers can switch to PEG parsers and not have any problems. So in 3.9, no new language features are going to be there. An LL1 parser can still parse 3.9, but probably not 3.10.
So for folks who are in the process of updating their code from 3.8 or 3.7 or what have you up to 3.9, what are some of the possible edge cases or bugs that they might see because of the introduction of the new parser that they would then want to fall back to the old LL1 parser?
Hopefully no errors are going to be there. So the hope is, of course, that for positive input, that means for valid Python programs, we do not have any bugs. But yeah, today showed that we do have actually some of them. It's a thing Pablo mentioned before, that we do have some bugs. Probably the most edge cases lie around the meta information the tree has. So there might be some cases where the actual position of the token for that was parsed by the parser is wrong. So maybe for multi-line strings or stuff like that, syntax error that might appear might show to a different place. But that's actually only for negative input. And I think we've made a good job of verifying that we're going to be able to parse 99.9999% of valid Python programs. And there's going to be some edge cases we've missed, and there's going to be some bugs we weren't able to discover, but I think that it's not going to be that much. When it comes to syntax error and meta information about Python parse trees, it's going to be a different story. I mean, I'm sure we've covered most of the cases, but there's going to be some edge cases there as well. And because it's so difficult to be sure that you've covered everything, I think there's going to be some bugs there, but yeah, hopefully they're going to be reported and we'll be able to fix those in time.
One important thing here is that, like, one story that happened before with the previous Python, like Python 3.8 previously, is that all this meta information that Lysandros was mentioning, unfortunately, even for positive parsing cases, was wrong. This is a well-known thing. It was pretty annoying because remember, the code that actually injected this meta information is this super gigantic file that now is gone, this ast.c. It was handwritten, and handwritten code is very likely to include bugs and inconsistencies, and there were plenty of them. I think some of the PyPy folks were working on something that was underlying in syntax error what part of your expression actually is raising the error. So you have function A plus function B, so it tells you which function is actually raising the syntax error. And they found some problems because the actual meta information that we were reporting was wrong. The good thing now is that because we are generating the AST automatically, this meta information for the positive parsing is correct. We actually find a huge amount of them and we correct them. We correct them also Python 3.8, the ones possible. But now all this meta information is much, much higher quality just because it's not handwritten. So, like now tools like this one that I was mentioning is now possible. For negative parsing cases, as Lysandros was mentioning, it is possible that there may be some errors as well. And, please, if you find any, report it to us. People that, for instance, run and maintain linterns and codes that check the source and reason of the source, like, Black, Pylin, Flake8, all of these, they care about these things more than users will, for certain. So they are already raising some of these to us. But in general, we have a lot of confidence, right? Because we only not have the information from the standard library for negative cases that we have, which again is not as much as positive ones, but it's a bunch of them. But we also run the test suite for Flake-8, Piling, and a bunch of them. And we some of these folks reported to us some of the errors that they found, and we corrected them. So it's possible that there may be some more, and I'm certain they will be. We will fix them as soon as possible, but we are pretty happy, I think, with the state of that. So people shouldn't be afraid that, oh no, now my syntax error going to be reported in Mordor. That won't happen. It's fine. There will be good syntax errors.
Of course. And it's pretty important to note that all these bugs we found during development of the bug parser in 3.8 and previous versions were never discovered by users. So it's not going to be that someone finds a new syntax error out of the blue. That's not going to be the case. Yeah, as Pablo said, we're pretty happy with our error reporting, and we hope that it's going to be even better in the future.
Yeah, I'm definitely excited to see improved syntax errors that do a better job of pointing specifically to the point of the program that threw the error versus what you were saying before, where it has to go through 2 additional layers of processing before it then has to try and backtrack to see where it went wrong with the parsing. And the other point that you made, tools that tie directly into the AST, I'm wondering if the removal of that AST.C is going to simplify their work for staying up to date, most notably thinking of things like Pylint and Asteroid, where there's usually a little bit of a lag between when a new release of Python goes out and when they're able to lint that code because of changes in how the AST is generated and the changes within the AST itself, or any other projects like Hi that is a Lisp that compiles to the Python AST, for instance.
That is kind of a different problem in the sense that we expose AST, which, as you know, all these tools use. Like, we say we have a way to these tools to obtain the AST directly in a Python form. But as you can imagine, precisely because grammar changes, and also we find some new optimizations, the output of the AST.parse function, which is the one that parses the AST, may be different between minor versions. That is the main reason there is also always a lag between a new release of Python and these tools releasing new versions with support for the new versions, because sometimes we need to change the AST. That is independently of the parser technology. It's just how we found some new grammar. Obviously, there may be some AST nodes now, but sometimes we change the nodes. It used to be that we have different nodes for numbers and strings, and now we have a single unified node called constant. So they need to change that, unfortunately. So that is one thing. The other thing is that normally, unfortunately for the errors, it was true that they needed to read this horrible file, as you mentioned. But in general, we try to do our best to notify these changes in the what's new document for a new release. So 3.9, for instance, you go to the what's new, any change on the AST will be documented there. So in reality, in a fantastic world, all the things that these maintainers of this tool need to do is to go to the what's new, look at how porting Python 3.9 or something like that, and there will be all the things that they need to change. I mean, I'm certain maintainers listening to me, they will be like, grabbing their pitchforks and torches, but because they probably will need to do something different, and we are sometimes inconsistent, but we try to do our best, so we document this there, right? Unfortunately, even with the new peg parser, there will be some delay on this, maybe even bigger if we introduce new grammar rules, right? Like, for instance, Python, even nowadays, is not even to parse the walrus operator, because the walrus changed fundamental assumptions on their handwritten parser, particularly that some nodes were final and couldn't take assignments and things. And unfortunately, like, for instance, in 3.8, Python is able to use the positional only argument syntax that I introduced, but not the walrus operator, because the walrus operator was a huge undertaking of their parser. So unfortunately, these folks will need to, adapt in some ways. Hopefully, if they need to find something weird, now there is a single file they need to go, right? Which is the grammar file, which is what describes the AST now, which I think is an advantage. But I don't expect any super quality of life improvement in that regard, unfortunately.
As we've discussed already, because of the fact that we do have this new parser with a more expressive grammar available to it, it makes it possible or easier to introduce new syntax that was too cumbersome or too impractical with the LL1 parser. I'm wondering what the scope of those new capabilities are, and if there are any specific features or PEPs that are planned for implementation in the 3.10 release that are relying on this new parser.
We all know about pattern matching, new peps about pattern matching. They rely on match being a soft keyword, which means that match is going to be a keyword only in the context of a match statement, so that code with match as variable names does not break. And that's only feasible because of the new parser, where we've implemented the feature of soft keywords, which can handle soft keywords pretty easily. It was not that hard to do. I think, and Pablo can correct me if I'm wrong, in the old Parser, that was not possible to have soft keywords like that in such an easy way. We used to have async and await being soft keywords, but there were many hacks around things like that. And now it's pretty easy to implement those. Pretty readable for someone to skim through the code and find out why this works. Something other than the match statement, which is not accepted, by the way, yet.
The parentheses with the statements. Don't forget about those. That's the whole deal. Who cares about match statements? Like, the important thing is those parentheses. I'm joking. I mean, that is obviously a small thing, but as you can imagine, I'm very excited. One of the things I want to complete about what Lysandros said is that, so it's true, it was not easy to implement this soft keywords feature on the old parser. I mean, it was kind of possible because, as Lysandro mentioned, async and await was soft keywords. But the way we hack around that is that we made async and await its own tokens. So normally when you have a variable or a keyword, so the tokenizer, which is this part that, the first thing in the parser is this tokenization, which is basically grabbing your source code as a bunch of bytes, and then it creates these items called tokens, which is basically words, but with some information. So for instance, it says, okay, this variable is called Bletch, is a name or is a keyword or is operation, like the plus sign, for instance, right? So the tokenizer was normally when it found a variable name like async or await, so either it says it's a keyword or either it says it's something else. In particular, before async and await were anything, it says it was a name, like any variable. Any variable is tokenized as a name. But for this async and await, the trick was saying, okay, async and await are now going to be this new special token called async and await. And that was now feed into the parser, and the parser, can distinguish if async and await is used in a context of a keyword or not. Hacks around, like, even if you forget about if it's a hack or not, the main problem is that your tokenizer should be independent of your grammar. Like, that is it's not only quality of life, that is like all theory of parsing is giving you. I mean, there is some super complex parsing technique that is called tokenizer feedbacks, in which the tokenizer asks the parser what kind of token this may be, and the parser can tell you different kind of tokens depending on the context. That is a thing. Like, it's certainly, if it's possible to do, someone will do it. But in general, in the normal parser world, the tokenizer doesn't know anything about your grammar. You can actually have different grammars for the same tokenizer. And then the actual thing that raises like meaning to the tokens is the parser. The parser with a grammar is the one that will tell you, okay, this word is now an assignment, or is a keyword for a for loop or something like that, right? So it was a bit of a hack because the tokenizer was cheating, and it knew that async and await is something special, right? So it was saying, take care of this, right? And I don't know what to do with this. It's async. I don't know what to do. And then the parser was saying, okay, if this is async and it's in a context, and this was 3.7, right? Because this was when async and await were soft keywords as well, because it was a time when async and await were introduced. Actually, I don't know if it's 3.7 or 3.5. Well, anyway, the first time async and await were introduced, I think it's 3.5. So in 3.5, let's say it's 3.5. The first time they were introduced, you can still assign to variables called async and await. And this was to not break everyone on the first try and giving them a release, right? And then in let's say it's 3.6, the first time this happened, I may have these dates wiggling around, but in 3.6, we made them strong keywords again. So you cannot now assign to async and await anymore, right? It turns out that MyPy still needs the soft keyword technology to parse all Python code. So there is a way to make them soft keywords again, but as you see, it's built on hacks on top of hacks. So the main reason is that you don't want your tokenizer to know about things. And that's how we made it before 3.9 with the new parser.
And another interesting point to what you were saying about parentheses, but going in the opposite direction, is the idea that Guido briefly floated of reinstating print as a statement and not just a function call.
Yeah, and that is not only print, but basically it was not pretty easy to implement a grammar for Python where every function could be called without parentheses. So that could be done in the new parser relatively easy as well. Because the quick parser syntax is actually pretty strong and pretty powerful, and you can do hacks and things like that. So yeah, when Guido back then proposed to have to bring back print as a statement, he also showcased some code which implemented actually every function call being a statement as well. So yeah, that was pretty cool. Of course, it didn't make it into a PEP, but it's pretty cool to see that the new parser is so powerful.
Right. I mean, independently if you like the idea or not, you may argue that, it's better or worse. I will not say my opinion here, but I think it's a good statement to how powerful this new technology that we have, this parser is. I mean, again, it's not the most powerful parser in the world. I'm sure that, parser experts are saying like, oh, you choose a peg parser, you are so stupid or whatever. But like, look, if we have something that we are comfortable because it's easy to understand, it's easy to generate. Like someone that understands the grammar can run the generator and they don't need to understand how the parser, is generated or all the little details of the parser, right? As long as they understand the grammar, they can continue editing Python. So going back to one of the previous questions, now I realize that actually makes contribution a bit easier, right? But the important fact is that now this example also is how little code that you can add to the grammar, how many things you could do that were very difficult or impossible to do before. So I think even if you don't like this idea of, suppressing parentheses or not, I think it shows that it's a good statement on how healthy and, versatile is the new parser.
In the work of bringing in this new parser and figuring out how to integrate it into the runtime and what new capabilities it will enable, I'm wondering what you have found to be some of the most interesting or unexpected or challenging aspects of that work.
Yeah, the thing we've mentioned loads of times until now is that there were many edge cases when it comes to metadata about the tree. And I think that was the most challenging part, making sure that everything is correct and truly the parser parses what it needs to parse and stores meta information, right metadata. Yeah, I think that was the most challenging part because after we were done with developing the grammar itself, we spent about 2 or 3 months, I think it was, in fixing bugs and finding such edge cases and fixing those. So it wasn't an easy job. I think that was the most challenging part. A very interesting aspect of developing the parser was trying to make it as fast as possible and maybe a bit faster than the old parser. We tried some things out there. We also tried a custom virtual machine for the parser at one time, but that didn't work out. We tried out many different variations of rule reorderings because PEG has a prioritized choice operator. That means every choice gets tried out in the order it's written. You can reorder those rules and make them go faster or slower for a specific input. That means, for example, if it's more probable that a name will follow an equal sign, then you've got to choose the name variation first and follow that path until you fail, because that's the most probable one. And that means that for most of the programs, you're going to be faster. And I think that was the really interesting part of all our work. We spent lots of time on it, and it was pretty fun to work on that.
For me, I think one of the worst things that we need to deal with is that because CPython is done in C, the problem that when in the parser you want to put together a bunch of nodes that are of different types, the container that we had was doing type erasure. So basically we hold an array of void pointers, and those void pointers were actually things. So ideally, they are what you expect to be, but there was some times when, when developing the parser, we were returning the wrong thing or, some unexpected bugs. The problem is that the bugs related to this were manifesting super far away from that, like even in the compiler itself, right? Like you generate some AST, but the AST is corrupted because, something that you said is of node expression. It turns out that it was of node statement or something like that, right? And then it's the compiler that grabs that memory and says, I don't know what to do with this, and it's seg faults, right? This problem has given us so many headaches, right? It's horrible. I've been working recently, we've been working recently on adding type information to this, so should do proper typing and do some generics in C99, which is not elegant, unfortunately, because the language is not prepared to do generics, but we did our best. Now, if someone is modifying the parser, now they probably won't need to deal with this problem anymore, because the compiler will say, no, you are returning here this type, and now you are adding this to this thing. That's not possible. So instead of having to deal with super spooky bugs at a distance, now the compiler will raise proper, compiler errors, which is much better, right? But in the time, I think that was something that was haunting me at night. Is oh man, like these bugs are like insane.
As you continue to work on CPython and help to improve the overall language and bring in new capabilities, are there any other aspects of the way that it's implemented that you think should be reconsidered or redone in light of the changes in the capabilities of compute and the hardware that we have and the ways that the language itself is being used?
I'm going to answer this. This is it's a very good question. It's also very complex. Before saying what I think about this, I will want to say that in CPython, at least, it's very difficult to do any substantial changes. And this is a truth that many people don't realize when they propose new grammar rules or when they complain about things, right? Because several stuff, right? One of the problems is that we have a huge surface for a C API. So the C API is a way that you have to implement extension modules done in C or other languages that have API compatibility with C, and basically interface with interpreters. This is things like NumPy, right? Like NumPy is implemented in a mix of C and Fortran, and it interacts with Python using the C API, right? And this C API has a huge amount of functions. And we use it internally. It's not something that we only expose. It's something that is used internally in CPython. So sometimes we want to make some of these C API calls a bit better, but it turns out that we cannot because it will break these C extensions. For instance, there was this attempt to do something like PyPy, which is that you have a list of just integers. So instead of having Python integers inside, which is not like the best representation for it because it's an struct that has an object and a reference count and a bunch of things. Somewhere in that huge struct for the integer, there is the actual integer in C, right? For integers, not for longs. But like one optimization was, okay, so if the list contains only integers, instead of storing Python objects in that list, we could store the integers themselves and represent the list as an array. And when someone is asking for a specific integer, then we box it, which is that basically we create an object on the fly and we give it to the user, right? And if the user then appends something that is not an integer, then we box all the integers creating Python objects, and then we transform the list optimized version in the normal list, right? So that is a cool optimization because doing things like adding all the integers together or iterating of the list is much, much faster, right? Well, it turns out that we cannot because there is many C API functions that will retain pointers directly to the data in the list, unfortunately. This means that if we do this kind of weird list version optimized, it is incompatible with some of the C API calls. So we cannot do that. And the same way we cannot do this thing with this particular list, we cannot do with many, many other things. Like, think about this, right? Like, we talked before about the AST. Even when we change the AST, that technically we are allowed to, because, if you change the grammar, you need to change the AST or you optimize. All the people that are doing linters, Flykate and Black and all that stuff, all those people should start complaining and say like, oh, you're breaking like this and that and this other thing. I mean, again, I'm not trying to trivialize this. I'm very sorry, and we like our users and we do the best we could for them. But for us, it's a nightmare because as core developers, we are trying to provide a better experience for users, and make the Python interpreter faster. Like, speed is something that everybody wants, like, independently of who you are. And unfortunately, like, doing this in a way that we don't upset anything or we don't break something is hugely complicated, and for every possible way, for the AST, for the C API, even change the compiler. Like, what I tried to fix some super weird bug that it was before. The bug was that if you have some conditional that is always false, so you do things like if false and then something, the compiler was basically destructing that thing. It was saying, I mean, this is never going to be executed, I'm not going to generate code for it. But it turns out that if inside that if you have syntax error, the syntax error was not being raised. Was just like, whatever, I mean, who cares? But like, it's a bug technically, right? So I fixed that bug. But unfortunately, then the compiler was actually visiting those blocks. And coverage was reporting now that those blocks were being visited. And because now coverage was able to see those blocks, but the blocks were never going to be visited by a Python program because the condition is always false, then the total coverage of your programs was slightly lower because now there is this block that wasn't it before, right? And the coverage people, complain and say, oh, this is unacceptable, right? And I mean, without trivializing the error, I understand why it was like bad, and we fix it because we care about coverage and our users. I'm not trying to trivialize this, but I wanted to say that for our point of view, even changing the compiler, which is something that, users don't interact directly with the compiler, is super tricky to do in a way that, people don't break, or you don't do something different for some packages and things like that, right? So for the coverage case in particular, we find a more elegant way to solve this, and we solve it in a way that, solve the problem that we're trying to solve and make coverage happy. So that ended very well. Thank you, coverage people, to raise this to us. But unfortunately, it's super difficult. So I can go into what I would like to change, but it's a very difficult thing to do as a core developer, unfortunately. And I think that, people don't normally realize how complex it is to do improvements in ways that people are not broken. Like, if we have a faster Python but NumPy doesn't work, like, who really is going to be happy about this, right?
Lysandros, do you have anything to add?
Yeah, I totally agree with Pablo. It's a thing that most people don't understand, that it's pretty difficult to come up with a change and then implement it and not break people's code. And that's a thing that surely makes it much, much more difficult to implement new features, to change the language or change the grammar or stuff. And when we're working on Python core, backwards compatibility is always a major consideration, especially after the 2-3 change. It's something we always consider and makes changing the language much, much more difficult and cumbersome. In terms of what I'd like to see changed, now thinking of working on two main projects. First one is f-string parsing, and I think that that's the reasonable next step. With this new parser we have now, it could improve how f-strings are parsed, because f-string also need to be parsed due to the literals they have, the expressions they have, the format specifiers they have. Currently, they're parsed by a handwritten parser. We've had discussions of moving f-string parsing into the new peg parser, how that could make things even more maintainable and readable. And another thing we've had discussions about is better error reporting and how the peg grammar enables that, and how we could further customize our error messages and display nicer information to the user when they have a syntax error, and how we could make that experience better for users.
I realized I didn't say what I like to change. I will do it very quickly, so I don't talk a lot. But one of the things I wanted to, this is something that other coders were interested on, is to move CPython from a reference count language into something that uses a different garbage collector. So our garbage collector strategy right now is a mixture of reference counting and cycle hunting. And ideally, one of the problems that we have is that doing things like removing the GIL or adding some specific improvements in multi-threading is very difficult when you have reference counting. So ideally, one of the things I think is for CPython in particular will be important is to try to move. I mean, this probably will break a bunch of things, but so doing this in a way that doesn't break is going to be the difficult part. But moving this into a different kind of garbage collector, probably not compacting garbage collector or something like that, is something that I really look forward for. Unlocking new implementations, things like removing the GIL, for instance, but many other. That is probably very ambitious. The one that I really look forward, and we can certainly do it, I think, without breaking people, is to change how the Python compiler is handling signals. So unfortunately, right now, the way we handle signals makes some Python, this is surprising. I mean, I won't extend myself here because we don't want to be here all day. But one of the things that people don't realize is that technically, with a statement, if an exception is being raised, your exit function is being executed, right? That's the purpose of the with a statement. It turns out that if a signal arrives in a super specific moment, so it's super rare, but it can happen, then what will happen is that your context manager won't be called, right? And many other things can happen. Like if a signal arrives on very specific parts of the evaluation loop, very weird things can happen. I think Nathaniel Smith has a very good blog post explaining how this is a super big challenge and how this affects Trio, for instance. But it happens in many different ways. And this is because there is no way for the compiler to say, for instance, between this bytecode and this bytecode, you cannot handle signals because it's not safe. Right now, signals are handled some intervals between bytecodes, between every possible bytecode, but there is combination of bytecodes when we say not here. We cannot have like regions when we say please between this and this, not handling the signals because this is not safe. Things like try finalies or context managers or anything that involves like, going back to the stack or raising exceptions, that is very, very tricky. And that has some changes on how the compiler works, how it emits bytecode. So I really look forward to in the future work on this. I mean, I have other projects, as Lysandros mentioned, specifically the create better syntax error, which is probably what I'm going to focus with Lysandros and Guido next. But this is something that I would like to collaborate, for instance, with Mark Shannon or other people, because this is something that's been bothering me, and it involves some change in the compiler that I think is not insane to do, and that is a good improvement. But yeah, I mean, probably it's not the most exciting change for people. People may expect some other crazy things, but I'm a simple person.
Yeah, it's definitely interesting just to hear some of the feedback from folks who are hands-on with the CPython runtime on a regular basis, because as an end user of the language, there are different elements that are useful and helpful and maybe things that might be improved. But as somebody who is working with the actual runtime and keeping it maintained and up to date, I imagine there's a whole different set of priorities. And so it's always interesting to get that insight.
We try to get our users happy, right? Like, people need to understand also that we are humans. We are human beings and we do this in our free time. I mean, yeah, people know this drill, but it's true, right? We are human beings. We have feelings, something like that. And, it's not only that we have different targets that are users. Many people say, the core developers, they are in their own world and they don't know what users need or want. Well, it turns out that there is lots of users, right? And some users want something, and other users want something else, and no one wants things that are broken, right? And unfortunately, the things that we need to care about in the core development world sometimes it seems different, or sometimes we try to do things that users want, some set of users want, and the other set of users say, this is horrible. Why are you there's a lot of people saying, why you don't make Python faster? I mean, I work daily on making Python faster, right? Or Victor Stinner, which is one of the people that have dedicated more time on this. But it's so hard. And, it's not a false dichotomy, I don't know how that is pronounced, but it's not a false dichotomy that you say or faster or new grammar, right? Like you can have both or none, depending on your core developer time, right? So it's a complex thing, but I just want to say that we listen to everyone, or we try to listen to everyone. And even if you think we are in our own core developer ivory tower or whatever, we are people just like you, contributors that like you, that we are doing this in our free time. And we think or at least we try to understand what the users want, and we try to work towards that. Not the things that we're interested in only, but sometimes it's very difficult to explain that sometimes these kind of changes are needed before these other changes happen, or sometimes it's difficult to say, if you want this, then you are not going to have this other thing, right? Like people that say, I want more performance, then many people don't realize, okay, then you won't have NumPy for a while, and then say, no, I want NumPy, right? But I also want performance, and it's very difficult to say, well, that is not possible in an easier way, at least, right? A way to say, please be good citizens. We are just people like you, and we try to listen to you. And, we are friendly people. You can come to us and we will do our best, or at least Lysandros and myself, I know for a fact that we will do.
Are there any other aspects of the work that you're doing on the PEG parser and some of the new capabilities that it allows for, or your other work on the CPython runtime that we didn't discuss yet that you'd like to cover before we close out the show? Well, for anybody who wants to get in touch with you and follow along with the work that you're doing, I'll have you each add your preferred contact information to the show notes. And so with that, I'll move us into the picks. And this week, I'm going to choose the annual Python Developer Survey. It's going on right now at the time of recording. Hopefully, it's still going on by the time this episode goes out in about a week. So definitely recommend contributing to that so that we can get as high quality data as possible about the overall Python community and the ways that the language is being used. My other pick this week is the Jessica Jones TV show. Started watching that recently on Netflix and have been enjoying that story. So, if you're looking for something new to watch, I can recommend that. And so with that, I'll pass it to you, Pablo. Do you have any picks this week?
One show that I've been enjoying a lot is called Raised by Wolves. It's a TV series. I don't know where I'm looking at. It's very difficult to track if it's Netflix or Amazon series on HBO. I think it's HBO, but I could be wrong. Raised by Wolves, a very good thing. It's, I think, by Ridley Scott, if I'm not mistaken. I'm super bad at names, so I'm very sorry if I'm mistaken here, but I think it's Ridley Scott. And I think, although it mirrors a lot of the alien world, I think it's very interesting. It's very intriguing. It's sci-fi. If you are into that, I think you will like it. So yeah, 100% recommend. The Pablo seal of approval.
And Lysandros, do you have any picks this week?
Actually, I very recently watched Afterlife on Netflix, and I think it's a great show to watch and just think about things. It kind of gives me the feeling that it's the only show I watched recently that you can laugh and cry at the same time. I think it's great, and I'd definitely recommend it. I think it's written and directed by Rick Gervais, and yeah, definitely recommend that.
Well, thank you both again for taking the time today to join me and discuss your work on bringing in this new parser capability to the CPython runtime. I appreciate all of the time and effort you've put into that, and I look forward to taking advantage of the new capabilities that brings to the language. So thank you both again, and I hope you have a good rest of your day.
Thank you very much for inviting us. It's been a pleasure to be here.
Thanks.
Thank you for listening. Don't forget to check out our other show, the Data Engineering Podcast, at dataengineeringpodcast.com for the latest on modern data management. And visit the site at pythonpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts@podcastinit.com with your story. To help other people find the show, please leave a review on iTunes and tell your friends and coworkers.